Hi, my name is Hangsu Lee from University of Texas at Austin, and I'd like to demonstrate our tool for large-scale decentralized learning simulations. We call it Swarm. Many of you will be familiar with the existing works on decentralized learning algorithms, which can potentially support on-device training in pervasive computing environments. However, algorithm developers or machine learning engineers would want to evaluate these learning algorithms with real device in a large scale, but it would be very costly and awfully time consuming. So when testing the algorithms, existing works rely on simulations to evaluate the performance of the algorithm. However, they only run on a single machine, which is not enough to simulate a big number of devices, especially when using a large model. They're sometimes built to emulate real-world devices to benchmark algorithms against resource-constrained devices, or they emulate connection of devices based on network simulations or mobility datasets. However, these implementations are not really easy to configure, scale, or reuse. Let's say you're an algorithm developer who wants to test and compare different decentralized learning algorithms, and you want to see how these algorithms perform when hundreds and thousands of devices are involved. Well, if you take a look at any decentralized learning scenario, you see that there are merely a sequence of two kinds of actions happening. First action is the devices exchanging information, whether they're model parameters or some contextual information. Second is a device processing the model, such as on-device training, model averaging, and model compression. We can construct a graph containing either of these two actions as vertices and edges to represent the order or dependency of these actions. And these vertices, or actions, can be distributed to multiple worker machines, and they can be carefully scheduled so that the developer can see the final accuracy of the model as fast as possible. Or we can distribute them so that a worker machine can emulate devices' resource constraints. We're building Swarm to support these two modes of operation. So let's see what Swarm can do. Swarm is a simulation tool that helps developers to easily deploy simulations with the least amount of frustration involved in configuring the simulations. They can evaluate algorithms at a larger scale in a shorter time, as Swarm handles the deployment and management of worker nodes. Also, Swarm can run simulations that involve complex collaboration patterns, as they do in the real world. Now let's see how an algorithm developer would use Swarm. Well, they would first implement their own learning algorithm by extending a base device class in the Swarm package, and they would package it as a Docker container and give it to Swarm. Next, they prepare an encounter sequence, which is a time-stamped sequence of devices that captures which devices meet and collaborate and how long they're connected. So Swarm decouples encounter emulation and the actual execution of the learning algorithm, so it does not matter whether it is generated by a network simulator or collected in the real world, as long as it follows a certain formatting. And finally, they set additional simulation parameters such as what kind of model they're using or what kind of data set or optimizers and various hyperparameters associated with them in a JSON file. So the path to the encounter sequence is also set in the same file, and this file is used in Swarm command line interface to actually run the simulation. And let's see how this is done. So this is the Swarm command line interface. Notice that the command prompt is indicating the name of the cluster of worker nodes this simulator is currently using, and we'll also look into how this works under the hood shortly. You can also create a swarm, which means that you add a context where you can configure and run a single simulation. This JSON file configures an example simulation that involves 10 devices running opportunistic collaborative learning using MNIST with a very simple model. So let's check if the swarm has been successfully created and switch into the corresponding context. You can also list containers which corresponds to each simulated devices in a specific swarm context. Let's try running the swarm, and you can see the list of the simulated devices along with the identifiers of which container is actually used to run training tasks corresponding to those simulated devices. We also have a web application which is called Swarm Dashboard that can display the progress of the simulation in real time. So you can navigate into the simulations that has been run or currently running by clicking the name of the swarm on the left side. And this table shows the progress of simulated device, and it also visualizes the performance of the model on the right side with this graph. And you can also check the configuration of the simulation. So how does Swarm do all this? This is the system design of Swarm. The current implementation of Swarm relies on AWS Kubernetes service and, of course, Kubernetes to deploy and manage the worker nodes. The worker nodes are comprised of Kubernetes pods, which have one Docker container running a stateless server. The training tasks, which is a sequence of collaborations between devices, is sent to Kubernetes load balancer and distributed to these pods. Swarm also maintains AWS DynamicDB as a central aggregator for all simulated devices information, including the training progress and the performance. The Swarm State API makes the states of these simulated devices available to the outside world, which is then used by Swarm Dashboard. Please check out our paper to find out the details. In the future, we plan to test Swarm with different decentralized learning algorithms such as gossip learning. Swarm can even be used for other approaches that involves centralized entity such as federated learning, because a server can be treated as a participating device that only does averaging the models. We also wish to come out with a more efficient scheduling algorithm to run simulations faster and provide benchmark of the Swarm tool as well. We also plan to support a more realistic emulation of various resource-constrained devices. Thank you for listening.